This is a picture of a gigantic star cluster in our own galaxy. It's called Omega Centauri. It contains about 10 million stars, and we're only seeing a very small piece of it here. These are all old stars. They're about twice as old as the Sun. And you can see they fall into three different color classes. They're gold stars, and in fact, most of the stars in the image are gold, and that's the color of the Sun. But then there are very blue stars, and there are very red ones. Now, the color contrast here is real, and it's picked up by our camera. The blue stars are very hot. They emit most of their light in the ultraviolet part of the spectrum. That's one of the new bands we have on the camera. But very little in the red band. And the cool stars are just the opposite. They emit a lot of light in the red band, but very little in the ultraviolet. So just by looking at the colors of the stars in this kind of picture, you can sort them by temperature, and in this particular case, it also means sorting them by evolutionary state, because the temperature differences here are caused by differences in the internal structure of these stars and in the kinds of fuels they're burning deep inside of them. So by studying pictures like this, we learn about the physics of stars as they approach very, very old age. Now, the second picture is called the Butterfly Nebula. For obvious reasons, it looks like a butterfly. This is also a star in old age, but it's gone beyond the stage of the stars you just saw, and it's now beginning to lose its outer envelope of gas, which is drifting back off into space. And that's being lit up by the radiation from the collapsing star that's left behind. Now, in this picture, we took advantage of the special filters on the new camera to isolate the light of 5 different elements, and they've been color-coded separately here. So, for example, the red in this image is nitrogen, gas, and the blue is oxygen. Now, what you're seeing here is a critical phase in what you might call galactic ecology. It's the point at which material that's been chemically processed inside of stars is returned back into space, where it can form new stars, new planets, and, in fact, life on many of those planets. In this particular kind of star, much of the carbon that is in our bodies and in other life forms is produced and recycled into the galaxy. The third picture is the only one of something outside our galaxy. It's a group of other galaxies that is called Stephan's Quintet. It's about 300 million light years away. Now, the name comes from the fact, as you can see, there are 5 bright galaxies in that field. 4 of them are actually close together in space, but the 5th one is just accidentally along the line of sight to the others. It's nearer to us, and you can tell which one that is thanks to the beautiful resolution of the camera, because it's the one in the upper left here in the picture, the blue galaxy. You can see the individual stars in that galaxy thanks to the camera. The other galaxies are 8 times farther away, and they're too far away to see the individual stars. Now, all of the blue stuff you see in this picture is young by our standards. That means it's between 10 and 100 million years old in this case. The 4 yellowish galaxies you see in the frame are gravitationally interacting with each other. They're pulling together, and you can see that material has been pulled out sort of like taffy from some of these, and there's a spray of blue stars right in the center there, which has been produced by the fact that one galaxy is running into another there. This kind of an interaction is a normal step in galaxy building, and we expect that over time, long stretches of time, those 4 galaxies will eventually merge into a single big galaxy. Now, for the last picture, we're back in our own galaxy. This is a cloud of dense material which is being bombarded by radiation, intense radiation from surrounding stars. You don't see the surrounding stars. They're out of the field, but they're bombarding the cloud in the center. And that radiation is having 2 effects. First of all, it's evaporating and even disrupting the outer parts of this cloud. And that's what produces the filamentary structure you see there, the green and the blue colors. And at the same time, the radiation is compressing the cloud and inducing new star formation inside of it. We call this triggered star formation, and it happens all the time. Now, the young stars that are being formed there you cannot see in this picture, because in this particular color band, the cloud is opaque. But if you go to the new infrared band that our camera provides, you can see inside the cloud. And so if we could go to that, this is going to be a dissolve from this picture, which is taken in the normal visible bands, to one taken in the infrared. And what you'll see is that the cloud disappears to a kind of ghost-like appearance. You see lots more stars. 4 of the bright ones in the direction of the cloud are young stars inside that cloud. And one of them, the one more or less in the center of the picture, has these jets coming out of it. You can see these beautiful long jets coming out. That's material being blasted out at a very high velocity out from what's going to be probably a planetary system by the time this thing settles down. And we only see these kinds of activities in stars that are about 100,000 years old. So what you're seeing here is a very energetic infant star being formed deep inside this cloud.